So welcome to the computer vision classes. Uh, this class we would start discussion about Hough transform. Okay, in the last class we completed having a look at one of the edge detectors, widely used edge detector known as canny edge detector. Now we are going one more step ahead in computing the edges. So by the way, let me before going into the details of it, this is the paper, classic again, another very classical paper in 1972 published by Duda and Hart. I'm sure some of you might have heard these names, particularly those who are doing some machine learning related stuff. This is again a very classical book written by these two authors, Pattern Classification and Scene Analysis by Duda and Hart. So did anyone hear these names? Did you come across this textbook? Very, very widely referred textbook, this one. Okay, yeah, if not, it's you could take a look into it, at least skim through the contents of the textbook at least, right? So if you go to the Google Scholar and type this paper name which is given there, you would be getting more than around 8,500 citations. I think I just searched it a few days back. Okay, that's what that tells you how good is this paper. As the saying goes, the picture worth thousand words. Okay, along with I have a sentence as well. The sentence saying here, an edge is not a line. I want some of you to give an attempt on what we are trying to convey here, and probably that would set the theme for our class. So can anybody give it a try on what exactly we are conveying here, and probably what would be the objective of this Hough transform? From there we can derive.
I think we want to detect straight lines with
Mm-hmm.
using these edges,
Mm.
but always detecting edges would not necessarily give us straight lines.
Very good. See, many a time you can have edges that are, for example, lines. But when you use any of these gradient operators, for various reasons, you might not get the straight line. You would be getting the gradients, and these from there you are deriving edges, but the edges you are getting are not lines. But you have the a priori knowledge in certain cases. You what you want is in fact a line. And to generalize it further, you could say that there are quite a lot of contexts where you expect the edge to have certain parametric behavior, characterized could be by line, could be by circle, in some cases some template shape you have it. So how do you achieve that? That's the key objective of this Hough transform, through which you could parameterize the edges that you are going to look for. In the beginning, it may appear that we are restricting ourselves to parametric thing might be a big limitation, but it's in fact not. We'll be seeing in this presentation itself quite a few examples where what you expect can be parameterized. The shape of the edge can be parameterized. As you could see here, suppose if you want to get the edge of this mirror, all right, so you could see there are this being in the 3D world, some cup and with some objects like pens are placed before that, but you would ideally prefer getting this edge here. So that sets the objective for the Hough transform. So another example, you have already seen this while we were discussing about computation of gradients, that class using spatial filtering. Say you want to get the outline of this building, so you would be looking at edges something like this. So if you are using, by the way, if you are using the gradient computation and then followed by gradient computation as a part of your even canny edge detector, you would be ending up with something like this, right? But you would rather might prefer to approximate these things with straight lines and see an outline rather than having an image like this. Another example, this is the image of the corridor of a, well, maybe apartments or a hotel room, whatever it is, doesn't really matter. Here also, if you want to get the boundaries of the corridor, with respect to the walls or the doors there, you would rather prefer having here some straight lines here. That's what you would like to get. What could be the objective here? For example, you might want to track somebody moving there on the on that corridor, or you might want to do some fancy stuff like some augmented reality, where you might in the image want to keep some flower pot there, for example. Don't ask me why, just I'm saying what can be done there. Or it could be some surveillance reasons and other things which is more practical. In those cases you would rather prefer having the straight lines there. Another example, or couple of examples, look at here. Let's say some IC fabrication is going in the foundry, where you would like to make sure whether the particular components got installed there, okay, got placed there properly or not. So in that case also, to automate this inspection process of the fabricated chips, this could be, for example, very well approximated with some straight lines. One more realistic example here. You want to track the pedestrians on a given path there, could be for various reasons, right? You might, simple case could be, you might want to detect how many people are walking there and track them. A bit more sophisticated or fancy thing could be, you would like to detect some abnormality, abnormal activity going on there, okay, not so common activity. You have a whole algorithm, but before that, for that algorithm, as the initial steps, you would require the delineation of the path as well, which you could perhaps do it with straight lines. Of course, there could be cases where you might not be able to approximate it with straight lines, very much possible. Just that here we are looking at some examples where finding out the edges which are lines, where which are parameterized by lines, does make sense. That's what we are looking at here. Another example, let's say your friend from mechanical engineering have come up with a robotic hand which could place the pawns there on the chessboard, and you fixed a camera, and you computer vision guys have come up with a whole setup of like the camera and everything, and then a processing algorithm, and then you took some interface APIs from an existing program of playing chess, and then you could think of that you would be playing on one side, and this robotic hand moving the chess pieces from the other end. Quite possible, isn't it? So here again, another customized example of chessboard, where you would expect here straight lines. So once you get the straight lines, you could very much get each box or each square there, and thereby you could then of course figure out from the other edge detection what is that chess piece that is there, and perhaps then you could write a program which would call the interface by figuring out which is the current position here, and then doing it. Quite possible, isn't it? So that's another perhaps motivating example for line fitting of the edges. Hope you have got some motivation now to begin with the case where you want to fit lines, and more importantly, even when you do not see the lines fully. That's the most important thing here. Look at here, this, there is an obstruction here that's happening. This region, for example, right, the spawn is covering this line here, you won't be able to see. Again, similarly, this is obstructing the line whichever is there here. Still you want to get line something like this, okay? So that's the problem that has been posed. Again, Hough transform is not just for the line, we will at least see for line and circle in our course. So anyways, line being the good starting point, this is where we begin. Now the problem is to fit the lines. You are given this image and fit the lines. If you are asked to design it with whatever you just learned so far in computer vision, and on top of it whatever ideas you could come up with, what is it that you will do for doing this? So is the problem clear? You will be given an image like this, for example, okay, you are asked to fit lines here. What would you do? Just figure out the edges which are lines and draw them there. That's what you need to do. Or you are given an image like this, I want as an output something like this. What is it that you will do?
That are the different slopes of lines actually. the
Right.
last image.
Right. So, you, what do you mean by that? You want to somehow characterize a line in the first place if you want to find it out, is it not?
Yes.
Yeah, that's a good starting point. Now you further think about it. What you will do now? How you achieve that?
First, maybe we could get a map of the gradients in the
Hmm.
image, or the slope of the edges in the
So
image.
you mean something like
And
this, right?
yes, sir.
Okay,
Okay,
good.
yeah.
Okay,
And then
so now we
start
moved from
from,
this image to you find out some gradients now, right? First step is to find some gradients, and you get now you are in instead of being in this scenario, you are now in this scenario. From there, now I want you to get these lines.
Maybe actually those lines are going to meet somewhere. We have to find out that convergence point.
Not necessary here. For example, take this example, they are not meeting, isn't it?
Yes.
Yeah, so that doesn't work.
So maybe
maybe,
we should try and recognize which are straight lines and which are curves.
I don't want to worry about anything other than straight line. I'll also tell you one more thing. I would also have a, let's say, a threshold of it, a conservative threshold where I would get rid of maybe some, see, there are small things there. For example, on the floor, for example, assume that this textural small variations doesn't matter for me. I'll get rid of that also. Now you tell me. From that, I should just retain those which have straight lines. And I was also giving you a hint earlier that how do you characterize the line and incorporate that information here. That's going to be the crucial step here. See, even if I show you this, you would be able to say that, well, I want this line, I want this to be there, I want to be this. Okay. So what perhaps, how do you characterize and then how do you look for it?
Curvature, sir. Like a line doesn't have the other edges we are seeing. If we
Hmm.
extend it to like throughout the corridor, the carpet, for example,
Hmm.
those aren't lines because if we move like certain distance in one direction,
Hmm.
it curves out. Whereas
Yeah.
the edges we are
See,
seeing doesn't
no,
have
no, no, no,
curvature.
no.
It
That
has
is
like
not
a same.
that's not always true. For example, the railway tracks. Okay, if the railway tracks are this way, these are the two railway tracks. My camera is perpendicular to the railway tracks. Then they would meet. Suppose I kept my camera on top of the railway tracks. So the this is a optical axis is now perpendicular to the railway tracks here. Then they will never meet. Is it not? So that's the perspective projection. Inside, depending on the viewpoint, the parallel lines can meet, and there are also the directions. A simple example is just this. Okay, the lines are never going to meet. As simple as that. Parallel lines would remain parallel. The lines would never meet. So that is not going to work. Maybe I'll give you few more hints. First, how do you characterize mathematically a straight line is one thing, and then you look at what are the variables there and how you could figure out, and then I would tell you a keyword. So from there, try to interpret. I would say voting. Okay, that's the keyword I am telling you. And then look at the how you characterize the line, and based on that parameters, and doing some kind of voting. Okay, what voting you think about it? These are the key hints I would give you. From there, can you explore further? So how do you characterize the line?
We have slope intercept from like y equal to mx plus c, where
Right.
m is the slope and c is the line intercept.
Right. So slope and intercept. Let's call it as y equal to mx plus c. So a line can be uniquely represented given slope and intercept. These are the two variables there, right? Now, maybe I would just draw something, and let's see if that helps you to analyze it in more detail. So let me move into the notebook mode now. Suppose I have a point here. This is the capital X, capital Y. Let's say my point is X naught and Y naught. How are we going to characterize a line? We all know Y equal to mx plus c, m being the slope here and c being the intercept here. Suppose for a given point, this is image space, correct? In the image space, I have a point here. Let me call something else as, let's say, as Hough space for the time being, or maybe Hough has nothing to as such technically mean anything except that this transform has been proposed by Hough. So let me call it as transform space to be more intuitive, the name to be more intuitive. Now, what I would like to do here is, there are different lines. If I give you a point, okay, there are whole set of different points that, on the other hand, I know. So for example, I have given you this point of x naught comma y naught, isn't it? So what could I tell here? Y naught equal to m times x naught plus c. This equation would be for sure satisfied, except that these m and c can take various values, right? Now, from this image space, I want to move to a transform space where I would here have m and c. Suppose, let me take here m value. If I give you an m value, for example, for a given m values, what are the possible, how many values of c could be there? Is the choice of c unique?
It is unique, sir.
Right. What is the c value then if I give you m value? How do you know what is the c value?
Y naught minus mx naught.
That's all. Y naught minus mx naught. That should tell you the c value for a given point x naught comma y naught, that being a point. Now, what we do not know is even m value we do not know. The problem is that because see, each line has a different slope. What is the locus of all the possible mc values here for this given point? Can you tell me that? So I would like to consider here, for example, all values of possible values of m here, and compute the c values here, and then draw a locus or connecting all those points I want to connect. So what would be the locus of all those points? How does it look like?
Straight line, sir.
Very good. That's a straight line. Why is it so?
Like it's like another again slope intercept form, sir, with slope as minus x naught and intercept as y naught.
That's all. Look at here. See now, your y is c, for example, here minus m into x naught, right? Plus y naught. Okay. You could also, in fact, tell here that what would be this value. Can you tell me that? By looking at this equation.
Why not?
So how do you get that? For example, you make here your at this point your m is 0, right? This is 0, m is 0. So c is equal to y naught. That also you can tell. And of course, then what is the slope of this curve, by the way? Is that possible to tell?
Minus x naught.
Right, that's all. Minus x naught is your slope. Since I have drawn it in positive direction, I should have drawn, in fact, if I had drawn something like that, that would make a better sense there. Okay, of course, it's just an example I'm drawing there, but that would rather make a better sense there, because the slope here minus x naught, I have drawn here x naught as positive. Okay, that's why I'm just writing it. Okay, now, so what we got so far is, I have one point here, let's say x naught, y naught. Now, there is another point for me, x1 comma y1. Okay, this is another point. This is x and this is y. This is my image space. Now again, from here, I am moving into the parametric space, where I would take here m, here I would take c. Now, there will be for sure two lines here, right? What can you say about this intersection here? Is there any chance that they will intersect in the first place? If I give you 2 points, are they bound to intercept or no?
They will intercept, sir.
Right, they will intercept. Can you tell me what would this M and C values at which it is intercepting, what would that M and C would correspond when you look at them in the image space?
Line connecting those 2 points, x0, y0, x1, y1.
Very good. Very good. See here, from this point, I could draw different lines could go here, right? And one among them is this line connecting them, right? Similarly, for this point also, I could draw different lines going through that. And one of them could be this, where this line, which is passing through both, would of course result here in same M naught, let me call this as M naught and C naught value. So if you are varying the M value here and computing the corresponding C values, if you have 2 points, then the line passing through them, the slope and intercept would correspond to the slope and intercept for this intersecting point. So maybe I will, before asking you that for any clarifications, I would slightly rephrase my statements. Suppose I have a straight, hopefully that would make it more clear. In the XY space, I have a straight line. Okay. Now, if I represent this in the M and C space, what does that will be represented with? So earlier, I took a point in the image space and have seen its representation or a locus of its representation in the M and C space, its parametric space. Now in the image space, instead of having a point, I have a line. How will it get represented in the parametric space of M and C?
A point.
That's all. It's a point. So that's exactly what is happening here. So you have a line that is passing here. Okay. That line would be this intersection point. A point in the image space, if you move to the transform space for representation of it, all lines that are passing through that point in the parametric space of M and C, a line would be represented by a single point. If you are taking multiple lines passing through a given point in the image space, then all these points would correspond to a straight line here. On the contrary, if you have a straight line here, that could be simply represented by a point.
Sir, I have one doubt.
Yes.
Means this line, as we are drawing very ideally, all depends upon the means how well you are detecting the edges, the image.
Yeah.
Means this cannot be perfect sometimes,
Right.
most of time.
Right. We are going to come to
may
that.
not fall as a point most of time, I guess.
But if you look at each pixel, we have a discretized image at the end of the day. The digital image is a discretized image. The moment you are seeing it, the gradient, and if you are interpreting the gradient as presence of gradient or absence of gradient, then it is just a point. Okay, I have something like this. So wherever I am keeping a cross mark there, that is where in your gradient image you thresholded it. Beyond anything below some magnitude, you make it to 0. Others you retain, and you got something like this. Now you, from here, you think of the ways such that you could get something like this. You might be having, let's say here also. That's okay. Let me put some more. Now you tell me how you could figure out this line. See here, one way to figure out a line passing here is I would draw all the locus. I look at the intersection, okay, and take M0 and C0. You draw a line here that would in fact pass through them, right? It's a very trivial case. Now we are stretching that further, where assume that these are the gradient points. You want to find out at the end of the day something like this. Okay, and I want you to think now in terms of the transform space on how you arrive at that line. the cross marks are the places where you have points. For example, that is where the gradients are there. Okay, you think in terms of for each point what would be the locus of all points, and then come up with some idea on how you can fit this line.
Sir, we can plot M and C graph for we can make every line possible with every 2 points in the y and x graph,
Every
and we
1
will
point,
plot
I
them.
guess.
No, sir. Every 2 point, like we will
Okay.
join them, and
Okay.
we'll plot them on M and C graph,
Hmm.
and there will be one point where all the points will be clustered around. So that will
Okay.
be the one point where this red line is passing.
Yeah. See, the combinations are becoming too high the moment you have a lot of points. For each point, you want to take combinations for other points, right?
Yes,
With other
sir.
point.
Yes,
Oh,
sir.
can you just think in terms of point wise and say something there?
So maybe we can
Maybe I will,
calculate.
yeah, before you answer, maybe I'll further simplify this before we go to the general case. Okay. How do you get that line? See, all are on a straight line. I have given you little more stretched, little more advanced case, extended case, but still it is a easy to track compared to the above one. So how do you do this now?
Like for each point, we can draw one line in Hough space,
Hmm.
and then the intersection from which the maximum lines are passing. Like that will
Very
be
good.
considered.
Very good. Very good. See here, uh, as all of them are passing here, each one of these points, okay, what is the slope of them? Each of those points, the slope you have seen here is minus x naught. Okay, so those values are different here. If you notice, the slopes are different. So yet there is this line, right, where it passes through all these things. So there will be at this line, right? And of course, there could be some line, I don't know, I could be wrong, but something like this, it could be there. And you would see here, maximum intersections are here. Do you see that? So from the parametric space, you would do one more thing here. You cannot actually vary it continuously. So you create a bin of variations here with a, let's say with a delta m, you keep varying it here, and you, in fact, there will be slight variations here because actual one might be something close here, but again those points will be all around here. So you take a thresholded values here also. So whatever C you are getting here, that also you threshold it to these points, and then you go through the each bin here and you count number of points that are coming here. So maximum number of intersections would be there for this part, and that will give you this line. This again, this algorithm steps I will tell you in more specific terms, but before that I want to make sure you got the intuition for it. So hope now you could easily extend this to a scenario like this, where for example there might be some intersections here. See, for example, there could be a line passing something like this, there are two, so there will be some intersection point here, but the maximum intersections would be occurring, okay, at this point, in fact, which would correspond to this line. Essentially, number of intersections would be number of lines passing through here, number of points that this line is passing through here.
Excuse me, sir.
Yes.
Sir, what will we do if we have multiple lines? We need to fit multiple lines in that image, sir.
Yes, these issues are, all these issues are there. Those specific cases I'll come back. You are in fact very true. Let's say I might be having two objects like this in my image, right? Assume that again I'm just drawing the contours. You don't, so the right now the algorithm would put something like this. But what you are saying is you don't want this, rather you want here this versus this, right? Is that not your question?
Yes, sir.
Yeah, that's a problem here. Good that you noticed it. We will come back to that later. I was mentioning the term voting, if you recollect here. So what you are going to do here is you take the possible values of m here, okay, starting minimum, okay, m whatever the minimum value it can take and the maximum value it can take. Now you would compute with some distance here which would reasonably make sense to you. You would take those points here on that, accordingly you will discretize it. And for this, now what you are going to do, you have a you go through each point here. Let's say you have these points, you go through each point here. Now for this point, you first look at this slope value m naught. Let's call some slope value m naught. Now given this m naught, you could compute the C naught value, the corresponding C naught value, you can compute it. How do you compute it? We have already done here. The C value corresponding to that is y minus mx naught. Okay, so this has, so once you are taking a particular slope, there is only for a given point, there is only one value it can take here. That C you take here, for example. Then you take for this point itself, you use another. So let me, for your easy reference, let me write this equation here. C equal to minus mx naught plus y naught. C equal to minus mx naught plus y naught. Is it not? Hope I copied it correctly. Okay. So now I am going to vary this m. Okay. For each m I would getting a, so I have fixed now a point x naught y naught. Okay, I will vary this, and then each one would give me 1 point here. And of course this would be, we discussed now enough that this all possible things would, okay, this is what I have drawn is line, not line, but you there visualize a line there. Okay, something like that you would be getting. Now what you would do, you go from this point to now this another point here, okay, where you have a non-zero gradient. You again repeat the whole process here. You would be getting something like this. Okay, then you go to another point here. So here how you keep track of things on the y-axis for C is you initialize them. So here is my m value, here is my C value. What you do is you take a point x naught comma y naught. Okay, you might think it's only 1 point. So let me take instead, you have taken a point of xi comma yi. For that, you take this value corresponding to this bin, initialize everything to 0, this 2D array. You take this m, okay, and now you compute the corresponding C value would be somewhere here. Let's say this is where you have it. You increment its value by 1. Next, you change this m value. Okay, you increment it again by so here suppose that correspond to this value here, this C value represented by this bin. So increment it by 1. Okay, you do similarly here. Maybe you might be getting something here. You do it. Next, you go to another point. I is varying from 1 to n. So then probably you are getting something like this, your line. So you increment this, then you further increment it. Now you will have here count 2, for example. Okay, this you will have count 1 1. Okay, assume that there is another line coming like this for the x3 y3. Then what would happen, this would become 3 now. Okay, and this would become, first time it is coming, so this would become plus plus would become 1, this would become 1. So maybe later something else is coming here, so this would become 2, this would become 2. You repeat the whole thing. Finally you figure out that cell which has maximum number of votes, and that particular m naught and C naught, okay, would give you the slope and intercept of the line that passes through maximum number of points.
This line, if we are adding, if we're incrementing one particular block, uh, the only condition is that there should be, the line should be passing through that block, is it?
Right, see, this block is essentially telling you that there is a particular combination with that M and C. That's all. So essentially this drawing line, I have drawn it to tell you that there is in fact the locus of all the point, all the slope and all the possible slope and intercepts includes this part, this particular combination of this M and this C. That's all I'm telling there.
Yes, sir. So if we decrease the size of the block, the line becomes more accurate.
If you decrease this M naught value,
No, sir. Size of the block.
what is the block here? What do you mean by block?
Block meaning like you're writing +1 and +2, right? So
Right.
each and every square of the plane.
Right. You mean this plus plus operation you are saying?
Yes, sir. The square within which you're writing that. So if we decrease the size of that square,
okay.
so we'll increase the precision, right?
Very good, very good. Yeah, that's something I wanted to discuss a little later. So your point is, can I rephrase your statement as, what if I am modifying my delta M value? Is that your question?
Yes, sir.
Very good. We will come to that. That's a very important aspect. I'm glad you noticed again this point. So I will come back to that. For now, you assume that we have taken the right discretization. Okay.
Okay, sir.
Yeah, that's a very, very good point. You think about it. In fact, what would happen if I reduce it too much? What, don't answer me now, but you think about it. You even draw something and think about it. Okay. See, for example, there are also cases where I might be having slightly off things here, because the edge here you are doing some smoothing and that can have an impact. And on the other hand, on a very straight line, I might be having 4. Okay. This is one possible line. This is another possible line, but I would rather prefer this line than this line if I have to just find out one line. Okay, second priority, second line would be this one. So what would happen? And there could be another case also where I might be having a single line is one possibility, or in my case, instead of a single line, what I had in fact could be 2 lines of the, these could be, for example, the contours of a very thin object could be there. So what would happen when I am discretizing with a large value of M and small value of M? These are all the questions that I want you to think about them in detail. And by next class, tell me what would be the pros and cons of changing this delta M. By delta M is essentially this width. Okay, length or width, I don't know how you call it. This, how you are changing it. So that is what is going to dictate that. And of course, C naught also to an extent, because the how I am discretizing C naught also, that those are the two aspects there. So this is where I am taking values. This is where I am quantizing them. Okay, this is very similar to the way you have image. So these are all the points you draw. You don't have to program anything, but visualize things and try to get some inferences there, conclusions there on what would be the pros and cons, what could be different scenarios possible, and what would be the pros and cons of in changing this delta M, taking on one side very small, on another side very large value, and what would be the pros and cons of it on different scenarios that you have thought about. Okay. Sorry, can you repeat?
You also mentioned that we can detect lines which are not completely visible.
Right. See, that has that is something should be yeah, that's something that could be clear from here. See, I don't have here the points everywhere here. It's just enough if I am putting a threshold on number of votes I am getting, okay, for a particular cell. As long as I have enough samples on that, that would give me enough number of votes here. That's good enough. I don't have to have each and every point, because at the end of the day, I am simply looking at which combination of M and C got maximum number of votes. That is why it is perfectly all right if you have partial or significantly, I mean, some good and sufficient information, good number of samples are there, but it is not at all required that you have each and every sample here. Is that making sense?
Yes, sir. And the extent of the gap does not matter here. How long the gap is.
Very good. That's another issue that has to be well thought here. That's indeed an issue. Okay. See, sometimes we don't want it. It depends on the context. Suppose your object, you want to, if it is a single object, if there is see, there is no way we are taking that information here in the way we discussed this algorithm. This algorithm requires certain modifications to incorporate that information. Again, we will definitely have, we will spend some time on that. Okay, that's a very good question. Right, then I'll stop here for now, and see you again on Wednesday. Bye. Take care.